All right, so we are continuing with the conditional chapter or topic. We just finished 5B, and so we had started that last Sunday, and we did the denominator. Now we just finished the numerator. So Miku, it looks like you may have gotten it. I'm not sure. I see the difference between the one with an asterisk and one without. I'm just not sure why you have two answers, but
so the asterisks means like correcting the thing right above you.
is that what you got though, or
Yeah.
okay, so I thought maybe you were wondering where you went off, but yeah, so it looks like you did get the right answer. Great. So I'm not sure exactly what ended up being tricky for a number of you, but you know, be careful. It's a polynomial. Make sure you multiply through. If you do it in your head, make sure you're really good at doing it in your head. But in the end, you get this somewhat neat fraction of 29 over 768, which again, that's only the numerator. And so that's why in the last step, I had to divide that by the probability of x being less than or equal to 1/4, which we got last class. That's highlighted in blue, 31 over 256. Let me highlight both of these details in blue. And then our final answer, you can put in fraction form or convert to decimal, because the 256 does simplify the 768. So it actually does come out to a decent number. But either form is fine for me. You know, web work usually requires a decimal form. Questions before we tackle the last part on this problem? All right, so there's one last piece, and that is to determine the probability that y is less than x, given that x is 1/4. So x has a fixed value here. This is a conditional probability, and I just want to refresh my memory. Okay, so we have f of x, y. We also need f of x, and it doesn't look like we found that here. Let me see if we had found that in the last handout. No. Okay, so we need f of x. So let's go ahead and get that. So f of x, the marginal distribution of x, is going to require integrating y out. We had solved c to be 8 last class, so we have 8x times 1 minus y. Again, we're integrating with respect to y, so we're going to have a function of x alone. And we know that y is related to x, and that's given by the support that I highlighted in blue. And so if we manipulate that like we did last class, we could see that y is going to be bounded above by 1 minus x and below by 0. And so now we need to evaluate this. Integrating with respect to y, 8x is treated temporarily like constant, and we've got y minus y squared over 2, which again, we're evaluating y from 0 to 1 minus x. So this is going to give us 8x times 1 minus x minus a 1 minus x quantity squared over 2. I'm going to simplify this a little bit by factoring out a 1 minus x. And when I do that, I've got a 1 minus a 1/2 of 1 minus x. So that's going to be this term. This is 1/2 minus a half of x. And if I remember to bring this negative sign out front in, this is going to simplify to 1 minus a half plus x over 2. Which means that we have 8x times 1 minus x times 1 minus a half is a half plus 1/2 x. And you could just write that as 1 plus x all over 2. It's fine. In the end, it's not going to be important. We didn't even have to go through that simplification because x is conditioned to be 1/4. So it's at this point, I want to put together our conditional distribution. This is f of y, given that x is 1/4. Remember, by definition, this is your f of xy divided by your f of x. F of xy is 8x times 1 minus y. And we just got our marginal to be 8x, 1 minus x. Make sure you don't switch your letter. And there's a 1 plus x all over 2. So the 8x's cancel out. And then we are left with, I'm going to bring that 2 on top. We have 2 times 1 minus y. And on the bottom, we've got a 1 minus x squared. When you multiply the 1 minus x times 1 plus x, foiling that, you've got 1 squared minus x plus x minus x squared. So the minus and plus x cancel out, and it simplifies to this form. It's at this point where personally I would plug in 1/4 for x. You could have done it earlier, but now that we've accounted for the numerator and denominator, it seems like the best time. So when x is 1/4, we have 2 times 1 minus y, and 1 minus a 4th squared. So that's going to be 1 minus 1/16, which is 15/16. And that means this is going to be 32 over 15 times 1 minus y. So this is our marginal distribution when, when x is 1/4. Now we haven't answered the question yet. We've just kind of set ourselves up with a piece that we need in order to get this conditional distribution. In order to get the conditional probability, we need this conditional distribution. And so it's at this point I would say, okay, so the probability that y is less than x, given that x is 1/4, since x is a 4th, that means we want the probability that y is less than a 4th. Which means we want to integrate from 0 up to 1/4, 32/15, 1 minus y. So you have a polynomial. I'm going to pull that constant out, 32 over 15. And we've got y minus a half of y squared, which we are evaluating from 0 to a fourth. So we have 32 over 15, 1/4 minus 1/2 of 1/4 squared. So 1/4 squared is 1/16, multiplied by a half is 1 over 32, which means that this fraction, when you have a common denominator of 32, is going to be 7 over 32. Which simplifies nicely because the two 32s cancel out, and our final answer is 7 over 15. So I'm just going to pause for a moment to see if you have any questions. We've finished this handout. There's only one more lesson in this topic. So before we move on to that, I just want to be sure, find out if there's any questions on this or anything we've done so far.
I don't know if you went over this last class, I don't remember, but why do you use the support 0 to 1 minus x instead of 0 to 1?
So that did come up last class, right here. So we know that x is between 0 and 1 minus y, which means that x and y are dependent on each other. Their supports are dependent on each other. And so I need to manipulate that particular support to find what is y between. And what we got, and the work is over here, what we got is this, that that y has an upper bound of 1 minus x.
Yeah, okay.
I don't use y minus x for the lower bound is because that's going to bring x back into it. But in the end, we want a numerical answer. And so it's from the other support, this one here, that I know the lower bound for y is going to be 0.
Okay. Okay. Thank you.
Wait, you're doing it. Why is it dy again? Because you're doing it by y or something?
You're asking why we integrated with respect to y for part C?
Yeah.
Because we want a probability with respect to y. It's the probability that y is less than something. So that means we're going to have to integrate with respect to y. Y is our only variable left. Because even though x is listed, x is conditioned, which means x is no longer random. X is a fixed value. We happen to be given that that value is 1/4. So even though there's an x here, because it's conditioned to be 1/4, you can, and we did, plug in 1/4 for that x value.
Wait, so y is so random?
Yes, y is still random because it's not part of the conditioned area, the right side of that probability statement. That's why, Sydney, when we found the conditional distribution, it was only a function of y. So there's no more x lingering anywhere. So it wouldn't make sense to integrate with respect to x when we want an answer for a probability, which means we want a number. So we have to be able to integrate the variable that's left? Were there any other questions?
With the f of x comma y is 8x times 1 minus y.
Is that a question?
Yeah.
Why? Why are you not sure of that?
I don't know.
Look back
It
to
just
the
says
problem,
it.
Sydney, because based on what the problem is saying, you know that it's cx times 1 minus y. And then if you review the problem, you'll see in part A, we solve for c. So that's how I know what the joint distribution is. All right, so I'm not seeing any chat questions on the chat board. So I am going to move on to the last part. The first part of this section was, again, it was introducing you to functions of more than one variable, and we've really stuck with bivariate. What we just did was conditional distributions and conditional probability. So the only thing left that you haven't seen with two variables is conditional expectation. And so that's what this last handout is about. And so the general form shouldn't be too foreign. You just have that vertical line that's denoting conditioning. But the basic format that in the discrete case, when you want an expected value, it is the sum of what you are conditioning on, which in this case is the expected value of y, just based on this sample notation. The expected value of y given x is the sum of y times your probability mass function, or if it's continuous, it's the integral of y times the probability distribution function. And because these are conditional expectations, you need to use conditional distributions. That's really the only change. I don't put it here, but if you wanted the conditional mean of x given y, you would just flip your x's and y's. So the pattern holds. You can also get variance using similar idea as to what you have been using with the unconditioned versions. So the variance of y given x is the second moment minus the first moment squared. It's just those moments are conditional moments now. So it's the expected value of y squared given x minus the expected value of y given x squared. And then I wrote how you'd get the second moment for the discrete and the continuous cases below that. All right, so the basic idea shouldn't feel too foreign. The only thing that really has come into play is the conditioning. There are some properties that you may find useful. And I think at least one of the examples that we'll get to will show you how to use these. One property is that the expected value of a conditional expected value is the expected value of the unconditioned part. So the expected value of the conditional mean of y given x is just the mean of y. And the variance of x, you could also obtain by the variance of a conditional expectation plus the expected value of conditional variance. So it's a little awkward. It's kind of easy to remember that they flip: variance of conditional mean plus mean of conditional variance. That's how I remember it. The same holds, again, if you want the variance of y, you just flip your x's and y's. And so let's see which of these examples may happen to use these properties, but I just wanted to introduce it right at the top here. So let's take a look at this first problem. Let f of x be 1/10 where x can be 0 through 9, and h of y given x is 1 over 10 minus x, where y is x plus 1 up to 9. We want to compute the expected value of y given that x is 4. So over here, we want the conditional mean of y when x is 4. That's the whole goal here. So that's cool because that means that we need to know our conditional distribution, which happens to be given right there. So we already have that. And we're conditioning that x has a very specific value, and that value is 4. So the expected value of y given that x is 4, and this is a discrete distribution, which means this is going to be the sum of y, where y is being multiplied by h of y, given that x is 4. And that's because, again, we're conditioning on x being 4. Now I wrote y under the sum to the left here, and that's because since y's support depends on x, it goes from x up to 9, and we're conditioning on x taking the explicit value of 4, I know that y goes from 4 up to 9. So now I could start plugging in some details. This is the sum as y goes from 4 up to 9. And we're summing y times 1 over 10 minus 4, because x is 4. So that's going to be 1/6. But I just wanted to vocalize it so you knew where that 6 came from. The 1/6 is constant, so I could pull this out of the sum. And I am essentially summing y when y goes from 4 up to 9. Which means this is 1/6 times 4 plus 5 plus 6, 7, 8, and 9. So you could do that in your head or with a calculator, either is fine with me. So 6 and 4 is 10, 15, 22, 30, 39 over 6 is the answer that I'm getting. Check my math, or are you getting something different or same? All right, I double checked it, so it seems like it came out all right. And if you wanted to convert that into decimal form, that is going to be 6.5. It happens to come out to a pretty nice decimal number. All right, I know it's just the first problem, but are there any issues with my reasoning as to how I talked through doing this problem? Did it flow, or did anything seem magical?
I thought it was good.
All right, thank you. All right, so let's take a look at the next part then. This is another one you've seen before. We're just doing something different with it. It says, let the joint PMF of x and y be as given. X goes from 1 to 3, y from 1 to 2. Determine the mean of y when x is 1. And so this is asking for the expected value of y given that x is 1, which by definition is the sum of y going from 1 to 2, and that's because that is the support of y. It doesn't depend on x like the previous problem, of y times the probability of y given that x is 1. Now, we don't have that conditional PMF yet, so we need to get that. The marginal I'm going to do up here. So we need the probability of x, and that means we're going to sum out y. And we may have found this in a previous lecture handout, but it's pretty quick to do over again. And so we have x plus y over 21 is our joint distribution. When y is 1, we have x plus 1. When y is 2, we have x plus 2. So that's going to give us 2x plus 3 over 21. And now we need the probability of y given x, which again is the joint distribution over the marginal of the variable that's conditioned, which is x. So the joint is x plus y over 21. The marginal we just got to be 2x plus 3 over 21, which happens to simplify to x plus y over 2x plus 3. So now I'm going to make use of that, and I'm going to plug that in to where we started. The sum is y goes from 1 to 2 of y times, now x is 1. So I'm going to let x be 1 because x strictly equals that. It's not an inequality. So that means we have 1 plus y in the numerator, and we have 2 times 1, which is 2, plus 3, which is 5 in the denominator. And so we're going to sum up y plus y squared over 5 as y goes from 1 to 2. So all that's left is to act on this summation. So when y is 1, we have 1 plus 1 squared, or 2/5. Plus, when y is 2, we have 2 plus 2 squared, which is going to be 6 over 5, which means we get 8 over 5, or in decimal form, 1.6. So that is our expected value, or the mean of y when x is 1.
Sorry, could I ask a quick question?
Yeah.
It's actually about the previous one.
Okay.
So we're given h of y given x.
Mm-hmm.
So because it's discrete, is it like obvious that the h of y given x is a p of y of x, or p of y given x?
Yeah, so these, even though the notation differs, you've got a conditional distribution of y given x. The label up front is different from my standard notation. Just like the little f of x is a marginal distribution that's discrete. I know that because of support, even though I tend to use little f for continuous. So it's with the information that's given, you should know that that is a conditional distribution of y given x, even though it's h and not p.
Okay, yeah, thank you.
You're welcome. Any questions on problem 2? All right.
Wait, where did you get 1 plus y over 5?
That is because above that in blue, we have the conditional PMF of y given x. But over, so here we have the conditional distribution of y given x. We want to use that here, but we want x to be 1. So I let x be 1 here. And when you do that, what do you get?
Oh, I guess. So,
Sydney, do you see it?
Is it? Oh, okay. Yeah. But you use y equals 1 to 2 because you're defining y or something?
Because the mean is with respect to y. So you're using y's support, which is 1 and 2.
But you know when you're finding like the marginal stuff, don't you have to do the opposite?
When you're, ask that once more.
You know when you're finding the marginal stuff, you have to do the opposite, yeah? Like if you're finding p of y, you have to do the x.
Yeah, I did right here. When I found the marginal of x, I summed over y.
Oh, but if you're finding the mean, it's like you sum over the same thing.
Yes, because that is when you're actually finding a mean, an expected value, then you have to actually use the variable whose mean you want. Otherwise, you're going to get an answer that still has a letter in it, a variable. It won't be a number. All right, so I'm looking at problem 3 now. And this is a continuous scenario. So it says, consider the joint PDF f of xy equals 4/3 of 1 minus xy, where x and y are between 0 and 1 or equal to. And I give you the marginal distribution of y in this case. So the marginal is 4/3 of 1 minus y over 2. Y is between 0 and 1. So in part A, I want to know what is the mean of x when y equals 1/2. So that's our challenge here. We want the expected value of x when y is 1/2. And since these are conditional distributions, that means this is the integral of x, because it's the expected value of x, times the conditional distribution of f of x given y is 1/2 dx. And so this is going to integrate from 0 to 1. So the one detail I don't know is what is f of x given y? What is that conditional distribution? How do you find that?
Is it f of xy over f of y?
Mm-hmm. And we happen to have both of those. So I'm going to do that on the side here. F of x given y is by definition f of x comma y over f of y. And again, it's y on the bottom because that is the variable we're conditioning on. The numerator is 4/3 1 minus xy. And the denominator is 4/3 1 minus y over 2. And the 4/3 cancels out, so that's nice. The next step is I realize that the conditional distribution we want conditions on y taking an explicit value of 0.5. So I'm going to substitute that in on the right. So that means we have 1 minus x over 2 on top. And we have 1 minus 1/2 over 2, or 1/4, which is going to be 3/4 on the bottom. Or multiplied by the reciprocal, we've got 4/3 minus 4/3 times x over 2, which is going to be 2/3 x. So it simplifies pretty nicely. It's at this point where I'm going to sub back into the integral we set up earlier. So this is the integral from 0 to 1 of x times that line, which is going to be 4/3 x minus 2/3 x squared. And so when you integrate this, you've got 2/3 x squared. I canceled out a 4 over a 2, or I minimized because of that. And then you have 2/9 x cubed that we are evaluating from 0 to 1. When it's 0, I see that this is 0, so it's great. I just need to look at it when it's 1. And when it's 1, it's going to be 2/3 minus 2/9, which with a common denominator of 9 is going to be 6 minus 2, or 4/9. Any questions, or so far so good? All right, so again, I trust that that silence either means that you're absorbing or that you're liking it so far. All the examples we've done so far have conditioned on an explicit value. So x or y have exactly equaled some number. And that's the easiest scenario. Part B here gives you exposure to what if you're conditioning on a variable being in some interval. And so you've seen something like that with conditional distributions and probabilities. You just haven't seen it with conditional mean yet. And so that's what we're about to tackle. All right, so let's take a look at this. I'm going to start by setting up what I need, or what this means by definition. So this is the integral from 0 to 1 of x times the conditional distribution of f of x, given that y is between 1/4 and 3/4. dx. So I need to figure out what is that conditional distribution, because I need to know what do I plug in there. It is not what we got up in the top right in blue, and that's because that really only works when you have an explicit condition value. So what I know is that this is going to end up requiring that we know what the probability is that y is between 1/4 and 3/4. And we happen to have the marginal distribution of y, so I'm going to make use of that. So I want to integrate that marginal distribution, which was given as 4/3 1 minus y over 2. And I'm integrating from 1/4 up to 3/4. And that's just because that's the probability statement that we want. So what does this give us? This gives 4/3 y minus, let's see, that's going to be 2/3 y squared over 2, which is 1/3 y squared I'm just making sure I didn't rush that too much. And we're evaluating y from 1/4 up to 3/4. So when it's 3/4, the first term becomes 1 minus 1/3 of 9/16. And the 1/3 goes into that to get 3/16 minus, when it's 1/4, the first term is 1/3, the 4's cancel out, minus 1/3 of 1/16, which is going to be 1/48. And then it's from here where I'd start simplifying. And so this first term, if I get a common denominator of 16, that's going to give me 13/16. And a common denominator of 48 for the second one will give me 16, 15/48. Now, if I get an overall common denominator of 48, I need to multiply the first term by 3/3. So that's going to give me 39 minus 15, which is 24. And so that means that we get 1/2. So it happens to come out to a nice fraction. Any questions about that piece so far? We haven't finished a problem. We just did an aspect of it. So far, so good. All right, so what does this mean? This means that the conditional distribution of x, given that y is between 1/4 and 3/4, is the joint distribution of 4/3 times 1 minus xy over that marginal probability that we just found, which is 1/2. Or we get simply 8/3 times 1 minus xy. So now we can substitute this in and we could solve. So I'm going to put that up here, even though I'm going to have to work on the bottom. So this is the integral. Now notice that we have x and y, which means that there's going to have to be two integrals. And we'll figure out those limits of integration in just a moment. So we have 8/3, 1 minus xy. And let's integrate x first and then y. In this case, it really doesn't matter because x and y aren't dependent on one another. I know that y has to be between 1/4 and 3/4, and y is my second variable that I'm going to integrate. So 1/4 to 3/4 are the limits of integration on this first integral that I wrote. And x goes from 0 to 1. And I forgot, I apologize, I lost my x in here. That is from just the fact that this is the expected value of x given y being in that interval. So we had an x up front that has to multiply through. So I'm going to go below in order to actually continue with this work. All right, so first we're going to integrate with respect to x. So that's going to be 8/3 x. Which when you integrate that, the x becomes x squared over 2. The 2 cancels, divides into the 8. So we've got 4/3 x squared minus, you've got x squared y, and there's still the 8/3 there. So that x squared becomes x cubed over 3. And so you're going to have 8/9 x cubed y. And remember, you're evaluating x from 0 to 1. We still have y left to integrate. And so evaluating from 0 to 1 simplifies pretty neatly. We're going to integrate 1/4 to 3/4. You're going to get 4/3 minus 8/9 y dy. And now we need to integrate this line. So we're going to get 4/3 y minus 8/9 y squared over 2, which is 4/9 y squared, which again, we're evaluating from 1/4 up to 3/4. So as you evaluate, you get 4/3 times 3/4, which is 1, minus 4/9 times 3/4 squared, which is 9/16. So the 9s cancel out, the 4 goes into 16 to give you 1/4. So that simplifies really nice. Minus, when y is 1/4, you've got 4/3 times 1/4, which is 1/3, minus 4/9 times 1/4 squared, or 1/16. So 4 goes into the 16, so that you get a 1/4 times 1/9, or 1/36. The 1 minus 1/4 is 3/4. The 1/3 minus 1/36 is going to be 11/36. And then when you get a common denominator of 36, I get 16/36, which simplifies to 4/9. It just happens to be the same answer that we got in part A. It's just, it just means something different. So in this case, we've got the mean of x, given that y is somewhere between 1/4 and 3/4, is going to be 4/9. That's your interpretation of B. The interpretation of A is that the mean of x, given that y is the value of 1/2, is 4/9. And so in one case, y had an explicit value. In the other case, y is some range. It's somewhere in that interval. So, did you guys get the same thing? I don't know if you were checking the math, the integration as I was working through. I tried to be careful, but it's great if I get confirmation that you're not getting anything differently. Thanks, Marissa. All right, so if on the side, later going through it, you do find that there was an error, please email me. I'm happy to admit a mistake and correct it. But I will trust that that we integrated the polynomials correctly. It should be thrilled to have polynomials and not trig functions, but but that's the answer that we get. So then we've got problem 4. And problem 4 is giving us a distribution that we've seen before. Again, we're just doing different stuff with it. And so here we want to compute the conditional means, which means we want the expected value of x given y, and we want the expected value of y given x. And we're not given any explicit values to let x or y be. So you are going to have an x in one answer and a y in the other. So let's go ahead and see what we get. Let's do the expected value of y given that x is some value little x. We don't know what that value is. It's just some value. By definition, this is the integral of y times f of y given x dy, and y is going to integrate from x up to 1. So I need to know what is that conditional distribution. I want to give you guys a chance to figure that out. So see if you could find f of y given x. We may have gotten the marginal distribution in a previous handout, so feel free to take a peek, or you could rederive it. I don't actually remember if we got it, but I'm going to pause the video here just to give you a moment to see if you could get that detail on your own. And if you do and you feel confident, then feel free to continue to evaluate this. All right, so does anyone have the conditional distribution of y given x? So that's when you divide by the marginal of y, Miku. Because remember, the denominator is the marginal distribution of the variable you're conditioning on. So here we're conditioning on x, which means you want to divide 2 by 2 times 1 minus x, the marginal distribution of x. And so you should get so I said 2 over 2, 1 minus x, so 1 over 1 minus x. That should be your marginal distribution. Yeah, that's right, Miku. Now we're integrating with respect to y, so that 1 over 1 minus x is essentially constant. Remember, x is a conditioned value. We don't know it, but it has some value. So this is integrating y from x up to 1. So that's going to give us y squared over 2. You still have the 1 over 1 minus x up front. You're evaluating y from x up to 1, which is going to be 1 minus x squared over 2 times 1 minus x. And then if you're clever, you realize that 1 minus x factors, there's 1 minus x squared factors into a 1 minus x, 1 plus x, which means that this simplifies into 1 plus x over 2. Now remember, x is a conditioned value. So what's neat is that if I were then to ask what is the expected value of y given that x is, let's do 0.5. What do you think you do to get that answer?
Just plug 0.5 into 1 plus x over 2.
Mm-hmm. Yeah. So you've got 1.5 over 2, whoops, which is 3/4. What about what's the expected value of y given that x is 0? And yeah, Miku, that's right. So Miku got 1/2, and that's because you have 1 plus 0 divided by 2, which is 1 over 2, or 0.5. And I put one more problem up here just for you to practice. So the expected value of y given that x is 0.25, and feel free to call out or post when you've got that answer. And yes, so Miku got 0.625, which I believe is 5/8. And so that's how you'd make use of it. That's why it could be advantageous sometimes to find and expect a conditional mean given, you know, some variable left in there. So some x or some y. So this way it's essentially a function. And if you wanted to know the conditional mean for any particular value, then you just plug that value in. We're going to go through the same process now, but we're going to do it to find the conditional mean of x, given that y is some general little y. And so I want to give you guys a few minutes to try to do this one completely on your own. And be careful, because if you're going to make a mistake, it's probably going to be in the limits of integration. And so, you know, think about that, give it a shot, and try to finish this problem through fruition, at least part A. Again, I'm going to pause the video and I'll return in a few minutes. All right, so I got 3 responses, and that does happen to be the right answer. So that's great that that you were able to get there. All right, let's go through just in case you didn't get that. So your setup should be the integral of x times f of x given y now, dx. And looking at the full support again, you're looking for the support of x, and x is between 0 and y. The conditional distribution in this case is going to be your 2 over the marginal distribution of y, which is 2y. So 2 over 2y is 1 over y, which is constant with respect to x. So this integral is 1 over y integral of x dx, which gives you 1 over y times y squared over 2. One of the y's disappears, and you've got y over 2. So that is your conditional mean of x given some y value. Now, I didn't write it in for these 2 answers, but obviously x and y are restricted, so they both have to be equal to or between 0 and 1. So you're not going to afterwards find the conditional mean of x given that y is 1.8, because y can't be 1.8. So there is actually a restriction on the values of x and y in each of these. It's good to keep those in mind. So if you weren't sure why I fictionally used the values of 0, 0.5, 0.25, I just need to make sure it was a value that was somewhere between 0 and 1, because that in the end is what the original support is saying. So that's it for part A. We haven't tackled B yet, but let's take a look at that. This is the first time that you're seeing variance or conditional variance in this case. So we want the conditional variance of x given y. That's what we're looking for this part here. By definition, this is the expected value of x squared given that y is little y minus the expected value of x given that y is little y. And that first mean is squared. Now we've just found that conditional mean. That's y over 2. So this is the expected value of x squared given that y is little y minus y over 2 quantity squared, which is y squared over 4. So that's this part. So now you need the second moment. So I'm going to pause again and give you a chance to find this because the process is the same as what you just did, except instead of the integral of x times the conditional PDF, now you need the integral of x squared. So go through, get that second moment, plug it in, and get an answer for this conditional variance. Again, I'll give you a couple minutes to figure that part out. So we're getting the second moment, which I've got in blue on the bottom. The conditional second moment given y, it comes out to be y squared over 3, which when you substitute back in appropriately to get your variance, you've got y squared times 1/3 minus 1/4, which is going to be 1/12. And so your variance is y squared over 12. Remember, this is the conditional variance. So this is the conditional variance of x given y. And so again, if you were asked what is the conditional variance of x given that y is 0.3, you would just let y be 0.3 and calculate what that comes out to be. If it's some other explicit value, you just substitute that value into this. So that's why your answer here is a function. You've got the conditional mean as a function of y.
Well, why is it y to the x squared?
Why is it 1 over y?
1 over y times y to the x squared over 3. I don't understand that.
Did you integrate?
Wait, wait, is that what it says? I can't tell.
Yeah, this is the integral of x squared dx. And that integral, when you evaluate from 0 to y, is y cubed over 3. Because x squared is x cubed over 3. And then when you evaluate, you've got y cubed over 3.
So wait, when you say second moment, you're always talking about the variance? Because it's not always the case, right?
The variance.
Huh?
The second moment is this first term in the calculation of the variance. The variance is the second moment minus the square of the first moment.
Yeah. See, whenever I heard moment, I kept thinking of the moment generating function stuff.
Yeah, if you had a moment generating function, you could find it.
I mean, but for moment generating function, I thought the second moment is the second derivative.
It is
Which is
from a moment generating function. But MGFs are just another path to finding a moment. They're not the only way to get a moment.
wait, so you could have taken the second derivative of this.
No, we don't have a moment generating function anywhere here.
Oh, you only do that when you have.
Yeah, that's why it's called a moment generating function. So it generates moments, but we don't have an M function here. We just have a joint distribution. We've got two marginal distributions, two conditional distributions, but nowhere did we ever get or were given an MGF. All right, there is one more problem left on this handout. So let's take a look at this one. This throws a few different things at you. First of all, it's a new distribution. You've never seen this one yet. An automobile repair shop makes an initial estimate X in thousands of dollars of the amount of money needed to fix a car after an accident. Let's say X has the PDF given here, which is 2e to the negative 2 times x minus 0.2 power, where X is from 0.2 upwards. So it's between 0.2 and infinity. Given that X is some general X value, the final payment Y has a uniform distribution between X minus 0.1 and X plus 0.1. What is the expected value of Y? So that's what we want to know. We want to know what is the expected value of Y. So first thing that I would do is I'd figure out, what do we know? I mean, we obviously know f of x because that's clearly given. But then you need to figure out, well, what is this uniform distribution? Does anyone know what has the uniform distribution? How would you write that?
Is it f of y?
Not quite. So it's related to y. It's not just y. Anyone else have an idea? What's missing?
Y given x equals
Y
x.
given x, yes. Because it says, given that x has some value, y has the uniform distribution. So this is y conditioned on x has this distribution. So that's the first challenge, is to set up what's given. Now, based on that, we know that this is a conditional distribution. And what is this PDF? Anyone remember how to get the uniform distribution? The PDF of a uniform? The uniform of A to B is?
1 over b minus a.
1 over b minus a. Good. So this is 1 over, our b is x plus 0.1 minus our a is x minus 0.1, which when you simplify, the x's cancel out and you've got 1 over 0.2. 0.2 is 1/5, so 1 over 1/5 is 5. So that's great. Now we have a conditional distribution. What else? I don't know if we need it yet, but that means that we could get f of x comma y also, because that is f of y given x times f of x, and we have both of those. So this is going to be 5 times the f of x function given on top, which is 10 e to the negative 2 x minus 0.2. And that's it. That's all that we actually know from this problem so far. So we need to figure out, how can we get at the expected value of y? So let me take a look at our shortcuts here, and I see that on the bottom, what I highlighted in blue, the first property gives me the expected value of y. The expected value of y is the expected value of the conditional mean of y. So I want to see if maybe I can make use of that. So let's see, what is the expected value of y given that x is some little x value? By definition, because this is continuous, this is the integral of y times f of y given x, which we have as 5 dy. And y integrates from x minus 0.1 up to x plus 0.1. So let's integrate this. We've got 5 halves y squared and y squared is being evaluated, or y is from x minus 0.1 to x plus 0.1. And so this is 5 halves of x plus 0.1 squared minus x minus 0.1 squared. And let's expand this because some things might disappear. So the first term is x squared plus 0.2x plus 0.01, 0.1 squared, 0.01, minus x squared minus 0.2x plus 0.01. And looking at it, I see that the x squares will cancel out, the 0.01 will cancel out, and then we are left with 0.2x plus 0.2x, or 0.4x. Which means you've got 0.4, which is 2/5 times 5 halves, which nicely works out to be x. So that's pretty cool, but we haven't finished yet. So we know that according to the property, the expected value of y is the expected value of that conditional mean and we just found that that conditional mean is x. So we need to figure out what is the expected value of x. And we have x's marginal distribution. So by definition, this is the integral of x times f of x, which we were given up above. And that goes from 0.2 to infinity. So this is the integral 0.2 to infinity of 2x e to the negative 2 times x minus 0.2 dx. And this is what we want to integrate. Now you can manipulate try to simplify if you want a few different ways, but I'll leave it up to you which way you want to do. So that power might be bugging you. You know, it's not an especially attractive power. So I'm going to choose to make use of use substitution initially. And I'm going to let u equal -2 times x minus 0.2, which means du is going to be -2 dx. And this part implies that x, if I solve for x, that is going to be 0.2 minus u over 2. All right, so now I'm ready to substitute in. And so the integral is going to be 2 times x is 0.2 minus u over 2, e to the u power, dx is going to be -1/2 du. I'm going to put the -1/2 here, du. And so there's a little bit that simplifies. And now we've got -0.2 times the integral of e to the u du plus 1/2 times the integral of u e to the u du. So you have the negative sign on bottom. When you multiply through, you have a -0.2 and a plus u over 2. I distributed the integral sign and I brought my constants out just to beautify what we actually want to evaluate here. And so you have a -0.2 times the EU, which is next to the DU, and you have a positive u over 2 e to the u. And so that's where I get the u e to the u du for the second integral. First integral is direct, it's a fundamental integral. And so that is going to give me -0.2 e to the u. The second integral you get by integration by parts or the tabular method. I think I've shown the tabular method before in the past. I'll do it again if you like seeing it, but you could use either approach that you may want. So let's see, u dv. So the u term is u, the dv term is e to the u. I take derivatives of the u part, so u's derivative is 1, derivative of 1 is 0. I stop at 0. I take integrals of the dv part, integral of e to the u is e to the u. Integral of that again is still e to the u. And then I multiply diagonally, where the first product is positive, the second product is negated, and if there were more, you'd keep alternating signs. So this means that this integral is u e to the u is the first product, minus 1 times e to the u is the second product. It's at this point where I would substitute back in for u, which is, let's see, -0.2 e to the -2 x minus 0.2 plus 1/2 times -0.2 x minus 0.2 e. You know, I'm going to factor out that e to the u just to save some space here. E to the -0.2 -2, excuse me. X minus 0.2. And we're evaluating this from 2.2 up to infinity. And so this is an improper integral. Doing it formally, I really should have converted it to a limit. But I trust that you guys know that. And so as x goes to infinity, the power of the exponential becomes more and more negative, or a larger negative value, which means the exponential term goes to 0. So that will go to 0 as x goes to infinity. And then the second term will also go to 0. You could use L'Hopital's to prove that. Minus, when I now evaluate this at 0.2, I see that the power of the exponentials is going to be 0. So it's going to be e to the 0, which is 1. So we've got negative 0.2 plus 1/2 times the x minus 0.2 is going to be 0 minus 1. This gives us the -1, and then e to 0 is 1. And so we've got negative times negatives. So these are going to become positives, which means we have 1/2 plus 0.2. 0.2 is 1/5, so 1/2 plus 1/5 is 7/10. 0.5, 0.2, 0.7. Yep, 7/10. That's our conditional. That is the expected value of y. Now, what does that mean in context? Because remember, this is a word problem. So we've got 0.7 as our conditional mean. Remember that the final payment y is a function of x, and that is in thousands of dollars. And so this really translates to 0.7 times 1,000, or $700. So the expected payment is $700. Or the final payment, the expected value of the final payment is $700. So that's how you'd actually make use of, of that property. It's a neat trick to recognize when to use it. I would recommend doing what I had done when I was thinking through this, which was I first wrote down what is given, what do we know? And again, the trick, in my opinion, it was this first step was to write correctly the information that was given. Because if you don't write that correctly, you're going to feel stuck and feel like, oh, well, I can't get, even if you went back up here and you were like, oh, E of y is the expected value of the conditional mean of y given x. And if you didn't label what's given correctly, you'd be stuck at figuring out, well, what is the conditional distribution of y given x? Because you need that to get the conditional mean. And if you encounter a situation like that, look back and think carefully, did you label what was given correctly? Because that may very well be the mistake that you made. And that is it for this particular topic. We've gone through everything you can do with conditionality. Any questions or comments?
Why did you have 0 plus 0 on the bottom?
Because that is what you will get as you let x go to infinity. Because the exponential function, the exponential function with a negative power.
Well, yeah, limit as x goes to infinity. Oh.
Mm-hmm. Yeah, then you're going to have e to the negative infinity. So in general, I'll just say e to negative x because it holds true regardless of what's in x. If you want the limit as x goes to infinity, this is the limit as x goes to infinity of 1 over e to the positive x. And so as x gets bigger, that exponential function gets larger and larger. And 1 over
Wait, hold on.
10 is 0.1, 1 over 100 is 0.01, 1 over 1,000 is 0.001. And so obviously it's getting smaller and smaller and approaching 0. So that's what's going on here. And then this second one with the x minus 0.2, that's going to be multiplied by that exponential. You could look at just as a general form, x e to the negative x, rewrite that as the limit as x goes to infinity of x over e to the x, and then use L'Hopital's. Which gives you 0. So those are your quick proofs of why the limits will be 0 for those parts. There's about 5 minutes left. I'm not going to go into to any new material, but what's coming up is it's transformations of random variables. And what that means is you now have a whole collection of distributions under your hand, you know, discrete and continuous. And so you may want to know, well, if x is uniform and y is e to the x, what's the distribution of y? And so you could derive distributions of functions of random variables. And that's what we're going to tackle beginning Sunday. So that's where or Monday, sorry, that's where we're heading next. I did post 2 more quizzes, one for this Saturday, and then the next one, I might be getting confused between your 2 classes. It's either Wednesday or next Saturday. I think I might put it Wednesday. So whatever I had said in the email notice or whatever Lalima had emailed to you guys, make sure that that you just read that and are aware of it. So it is it may not be on the standard day, but I'm happy to tackle questions with respect to the material that we covered today if you have any. If not, you're welcome to leave early. That's fine, and I hope you have a great rest of the week and weekend.
Wait, so this problem was y given x is equal to x. The big X is a random variable?
Yeah. Every capital letter in this course, Sydney, will represent a random variable. You're all welcome. Sorry, I'm not thanking you individually. It's just quicker this way.
Oh, okay. So you have, so I don't know. I just didn't understand this problem. I just couldn't follow along. I don't know. So